We're going to consider the superposition of a source and a sink. Say we've got a source of fluid here, so it's spewing out fluid. It's located at minus A0. And we've got a sink which is eating fluid at A0. The potentials for these things, you can look them up, or you can consider, like a constant outflow kind of thing, and integrate the velocities to find the potentials. We did this in the lectures. Or you could just write down the potentials as is here. If you're asked to compute the potentials, of course, you need to start with the appropriate definition of the u velocity for, or the velocity for a source or a sink, which is in polar coordinates, u equals q on 4 pi r squared 0. All right. The potentials, however, for a source is this. For a sink, you're going to just get a minus sign there, right? And that's going to persist there. So depending on the strength, right? We're going to take the strength, this Q, to be plus or minus 2 pi. So the source is going to have strength 2 pi. So we're just going to get log R for the potential. And we're going to get minus log R for the potential of the sink. The idea now is that velocity potentials exist in irrotational flow. If our flow is irrotational, we have a velocity potential, but also in an incompressible irrotational flow, we then have a velocity potential satisfying Laplace's equation. I'll just write in yellow here because it's not quite relevant to actually doing the problem yet. Because we have Laplace's equation, Laplace is a linear equation. Anything that satisfies this Laplace's equation can be added to something else that satisfies Laplace's equation. So we can, in the cases of a source and a sink, they'll individually satisfy Laplace's equation, and therefore we can add them up to get something that satisfies Laplace's equation as a combination. Right? This is the principle of superposition. We've got polar coordinates here, and we've got the center of the source, right? These are defined in local coordinates. Now, we don't want local coordinates. We want Cartesian coordinates. We want them all to make sense. So we're going to have to rewrite our potentials. Firstly, to be Cartesian, so I'll just ditch the q and 2 pi, because that's obviously 1. Log. Remember, obviously, that r is square root x squared plus y squared, but that still has the origin at 0. We want to shift to these local coordinates, so x minus a squared plus y squared, right? So we shift to minus a here, half. And for the sink, it's plus a squared plus y squared to the half, like so. Now we're in a position to add these things up and get a total overall potential. Oops, I forgot my minus sign from my sink. Because we've got a log of a power, we can take that factor of a half down. It's going to be on both of them. So we get log x minus a squared minus log a plus a, like so. Once we know the velocity potential everywhere, we know the velocities everywhere, since d phi dx equals u d phi dy equals v. Thus, we can compute the velocities everywhere, right? So if we're asked for the velocities over this this flow, we simply differentiate this expression. So I'll differentiate. I'll find v in this example. U is entirely analogous. I just can't be bothered doing both of them. It's not fun. When you differentiate log, you get 1 over the argument. Remember, since the argument involves a y, we're also going to have to use function of a function rule. That's going to give us a 2y when we differentiate with respect to y, so that's going to cancel half. Similarly, like that. Right, I could actually just do u. It's not that, it's really not actually different. It's just that. Once we have these, we can go and look for interesting parts of the flow. Usually interesting parts mean stagnation points in potential flows. That is where the velocities vanish. But you might be hard pressed to find a stagnation point in this particular flow. You can kind of sketch what the flow is going to be up to, right? You can contour the potential really, but if you've got stuff coming out here and going in here, all your things are going to have to get over here, right? So you're going to find a flow that sort of does this. You can put arrows on it as well, right? So in here you've got the sink behavior, right? Out here you've got source behavior and so on. If you wanted to get a more complicated flow, you could then impose another potential. You could add this to a uniform stream, for example, and get the flow over what's called a Rankine body. But yeah, that's how you get the velocities from velocity potential and through superposition.